Sorry, we cannot hear you if you're speaking. Yeah, there is no audio.
If someone in the classroom can hear us, maybe they can remind the professor. Thanks.
I was muted. Oh my God, this is terrible. So amateurish. Hello, can you hear now?
Yeah, thanks.
That's not quite normal. So sorry for. I was the bug this time. Okay, so I'll summarize a little bit what I just said. So we just said we have a control volume. This is here. We have a sink or a source. This is what's coming from inside. And then we have what leaves the control volume or what enters the control volume. And this goes through the boundary. Because we are in the continuum hypothesis, we can integrate that over the whole domain, which means that we integrate the total value of U over the domain. U is the quantity that we are interested in, let's say displacement or temperature. We take the total quantity over the whole domain and we differentiate with respect to time. That gives us the change in that quantity over the whole domain with respect to time. So if we are in steady state, meaning when time-dependent parts disappear, all that stuff disappears, and we have only the source equals the flux towards the outside, right? Or flux towards the inside, which makes sense. So now, what then I said is that you need to then figure out if you choose an approach where you follow all the particles, or if you decide to look at the particles going through a domain, which is what we do in that case, at the top case. And both cases have an advantage and drawback. I also shared some different presentations on different discretization schemes for those of you who follow the other class too, on material point method and so on the signal group, where I give a few examples of when you'd like to use this, when you'd like to use Lagrangian, and why. And this is the MPM, material point method, is one method that goes in the direction of unifying these two together. Okay, so then last time we said, what are the types of partial differential equations that we might have? And we said we can write a general partial differential equation, at least in 2 dimensions, as some coefficient times the second derivative, some coefficient times the mixed derivative, some coefficient times the other second derivative. And well, if you have other terms, because you have other directions in the problem, then you can add them. Then we said that there is a certain discriminant delta, and that delta is a bit like the quadratic delta, except that normally there is a 4 here, but in our case there is no 4. So it's b squared minus ac and not minus 4ac, because we have this 2b here, which compensate that. Because if you calculate b squared, you have then 4b squared, right? If b is 2b, you have then 4, and then the 4 is the 4, and then you get rid of the 4, and then you have b squared minus ac. I guess you can see it. So it's exactly the same, b squared minus 4ac, except that here we write 2b instead of having simply b. Right, so that's quite evident. Then now you have 3 different cases of partial differential equations, and that comes from the fact that you have conic sections, and depending how you cut a cone, you can get either an ellipse or a hyperbola or a parabola, and this will give you 3 different types of equations. So the first one is the cool one. When delta is negative, it's related to diffusion. And we started saying last time that in diffusive cases, all the points in the domain see each other instantaneously, and there is no speed of transport of information. It means that I start heating point A, and immediately all the points immediately know that I've started to heat point A. So today we're going to come back to that, I hope, in a clearer way for the case that I find particularly difficult, which is the hyperbolic case, simply because I mostly worked on elliptic and parabolic cases. So for me, hyperbolic is, as I draw here, a little bit scary. Okay, so the second case is parabolic when delta is equal to 0. And this is exactly the same as elliptic, except that you have on top of that some time. So you can imagine elliptic as a steady state. That means that the time derivatives are all 0. Nothing changes over time. So it will tell you a steady state temperature profile in a plate. For example, if you heat up a plate, you have a constant temperature on the boundary. And then you may have a sink somewhere here. Okay, so let's say you heat it up at 100 degrees and you have here central temperature is 0, right? So you can imagine what the temperature will look like. I can tell you it's going to be linear between 0 and 100 in that direction, linear like that, and that line. Okay, so if you take cuts, you will have linear solutions. That's what Laplace equation tells you. This is here not Laplace but Poisson, but the sink term, which is the central fact that you have either a sink here or a prescribed temperature at the center, doesn't matter, will give you a linear response in between, right? And so this is the way it will look, but that doesn't tell you how the temperature gets there. It just tells you at infinity, when time goes to infinity, if this problem was time dependent, let's say that instead of immediately rising the temperature to 100, I progressively rose the temperature to 100, or if I was interested in, let's say, initial temperature of the plate is 50 degrees, central temperature is 100, boundary temperature is central is 0, boundary is 100. How does the temperature evolve until it reaches steady state? That will be a parabolic problem. So another example, if you put any pollutant in an aquifer, you may be interested in knowing the long-term solution. So what will be once everything has dissolved and once it's been advected by the flux of the water in the aquifer, what is the concentration everywhere? And that would be an elliptic problem because you're looking at steady state. But if you're interested in, let's say, you have one measurement system, one sensor at one given point, and you want to predict what will be the evolution of that concentration of pollutant at that point over time, then you will need to solve a parabolic problem because elliptic problems know nothing about time. They only know about the steady state. So they will get rid of all the time derivatives and only give you spatial derivatives. And then you will have very nice solutions that look super smooth, very regular, and very well behaved. So that is in a nutshell what you should remember about these types of problems. And that's very useful because once you know an equation, you see immediately, if you see an equation like Laplacian u plus b of u equals 0, you know immediately that this is elliptic, right? But if now I write it again, Laplacian of u plus b of u equals du dt, well, then you know that that is parabolic because there is a change in time. And this is equally true because that thing here is simply the change over time of the quantity u, and this is compensated by whatever diffuses, which is the first term, this Laplacian u, and the second term, which is the source or sink of quantity u. So how much comes out and how much goes in because of external sources. Yeah, that's it. And then you have the third case, which is the hyperbolic case. And the hyperbolic case is, you can think of it as waves. So wave equations or transport equations, but only, yeah, waves. So in that case, you have time and space dependence usually, and the information travels at a certain speed, at a certain, towards a certain, in a certain direction. So you will see when we talk in a few minutes about characteristics, you will see that the information travels along the characteristics. And if you want to know what initial value you need in order to compute the current solution, you travel back on the characteristics, come back to time zero, and see where you are along the spatial axis. But we will come back to that, don't worry. Okay, so then again, now if we look at this in a sort of more detailed way, so the elliptic case is a second order partial differential equation. Why second order? Because we have here second order derivatives. So we have here two derivatives up and down. So this is a second order equation, and it has obviously boundary conditions. So this is called a boundary value problem also, as opposed to an initial value problem, for which you give the initial values and you look for the evolution over time. Here, you give the boundary values. That means that you provide the data on the boundary. So for instance, here and there, and you may have two types of boundary conditions. And this is something we talked about earlier, but it's always useful to be reminded of that. And you can have two and only two types of, well, actually three, but of boundary conditions. For now, we'll talk about two, which are Dirichlet and Neumann boundary conditions. So the Dirichlet conditions fix the value of the unknown field. So that means, for instance, if we're talking temperature, because that's easy to imagine, you fix the temperature of the boundary along a certain line. That would be this. The other thing you can do is you fix the amount of that thing coming in or coming out of the domain. And that will be a flux, and that is called a Neumann condition. This is what it is. And the Neumann condition, as we said, is a gradient of the quantity in the normal direction. So in order to know how much of something comes into something, you take the dot product with the normal. So for example, if you're interested in putting solar panels on your roof, you do not want to put the solar panel parallel to the light rays, because if you put the solar panels, let's say, like this, and the light comes like this, there will be no energy transferred from the light to the panel because the flux of light through the panel is zero. What you want is that the flux of light be perpendicular to the panel, because this is where the energy is transferred optimally. Why? Well, because you have 90-degree angle, right? So that means that the flux is maximum, right? Logical. So that's why some people even have solar panels that rotate during the day, depending where you are, such that the flux is maximized, and that depends on latitude and also where you live. And in Luxembourg, you can optimize whatever you like, because for 6 months there is no sun. So that's a special case. Okay, so you cannot predict all cases. Again, we repeat, if there is no time, this is steady state, and this is what is that type of equation. So the equation that I wrote here is known as the Poisson equation. So Poisson's equation. And the Poisson's equation is exactly the same as Laplace equation, except that you get rid of, I should find a proper, yeah, you get rid of the source. So Laplace is Poisson without source. So Laplace would be the same thing except you just have 0 here. So this is an homogeneous version of Poisson equation. In other words, there is no source, no sink in Laplace equation. And Laplace equation is super nice. It has hugely interesting properties. The maximum principle is very easy to solve. You can solve it on squares, on cubes, on parallelepipeds, on spheres, on portions of spheres, on cylinders even. And you find very nice solutions, Bessel's functions of whatever type, depending on what case. Then you have very, very nice solutions. They are always well behaved. They look very smooth like those here. And it's super nice. And last week, when I was working with colleagues in Exeter, I learned about a method which I didn't know at all, which came up probably a long time ago, but that people in computer graphics published 2 years ago in a computer graphics journal, which is based on to solve this. So here we're not solving theoretically, but I can't resist telling you about it because the thing is so cool. And I think some of you will be interested. So the idea is to do a random walk. So to solve Poisson equation, to solve Laplace equation. So it only works for Laplace. And the idea is that in order to, so it is based on a super nice property that if you start here anywhere in a domain and you have a problem which contains either Neumann or Dirichlet, but for now, in the last paper at least, tackled both cases. But if you just for now simplify to having only a case of Dirichlet conditions, and you would like to know what is the solution to the Laplace equation on that thing, knowing what the conditions are on the boundary. So it's quite admittedly a simplified case because you never have only Dirichlet and also Laplace equation. I mean, it's very useful in computer graphics for rendering, for example, but still it's quite a limited case, let's admit. But what is amazing is that let's imagine you do a random walk and you have 2 points. So random walk is a way to do some sort of statistical method which allows you to solve certain problems. Let's say that you go here and you randomly choose the length, of course, within a certain constraint and the direction in which you go. So you can imagine random walk looks really like this. You can imagine a little ant that walks around. It could somehow decide to do this and be close to that boundary and then suddenly reverse and having no idea where it's going, end up there. And then what you do is you store the value of the boundary that you hit after the random walk. And you store that value somewhere. Then you do likewise for the second point, blah, 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 and you go to another point, and maybe here the value is not the same. Maybe, temperature 2, and here temperature 1. So let's say that was T1 for that point, and T2 for that point that hits here. Well, the value in the middle is the average of T1 and T2. This is completely amazing. I mean, to me, it's a super nice theorem that dates back centuries. But to me, it seems completely counterintuitive that if you randomly walk from one point, hit a boundary, you don't know which one it's going to be, but on average, you will get the average value here of the 2 points, which means that you're exactly solving Laplace equation, because Laplace equation gives you exactly that. If you have the value here and there, the value in the middle is the average. Which is really amazing. And so we're going to study this in my group because I want to see if we couldn't maybe use that to simplify certain problems that we are looking at, because it's so beautiful that that I don't want to let it go. Yeah. Yes, it's exactly Monte Carlo. Yeah. It's also Brownian motion, in fact. And so I want to learn more about this because I find it really, I mean, I would not have, I don't know what I would have said if someone asked me, what do you get? The average, really? I mean, maybe, but maybe not, No, it's I didn't read everything, but I think it's a expected value. So it's really a statistical view of the problem. You do an infinite number of runs. Oh, someone is speaking now. Not anymore. Yes. Yeah, so yeah, they are fast and they can do things that have really, as far as I saw, they have a boundary mesh which is super fine, but not much inside, you know, and so they don't need to mesh the inside, which is an advantage. And I mean, they look at examples that are really, really beautiful things like a toast with all the intricate holes in it, with millions of vertices on the boundary. But you know, it's computer graphics also, so they usually show very beautiful pictures, but it's not always so clear what's going on in terms of convergence. So I really want to look at that, and with a colleague in Exeter, I think we're going to write a Marie Curie fellowship on that, so that someone can come and work on it, because it seems beautiful as just that very fact is to me very interesting.
A single point value that they compute with this, or a full solution on the domain?
No, they want the solution on the domain. Yeah.
Because I think it's very effective if you're just interested in, let's say, 1 point of the domain, and you need a solution for this one.
Yes.
You just sample one.
Yeah, good point. Yeah, I don't know. I'm going to read it in detail. I think I posted it on one of the Signal things, so that you guys can take a look at it. But yeah. Okay, so yeah, so the solutions look very smooth like this, and so that is nice. Then we talked also last time that they look smooth, these solutions, meaning that they are differentiable and so on, but sometimes because of the reality of the modeling process, you know, if you model an L-shaped curve or that sort of curve of boundary, you have essentially a problem, because this is a sharp angle which doesn't exist, as we said, because a real sharp angle does not exist in nature. So you very rarely, if ever, have one atom corner. Well, those, because they probably, I can imagine, because they are not physically meaningful, you end up with singularities at the corner points. So that means that the level lines of the solution, so you know, these lines here that you plot, they are themselves smooth, but they get together, you know, they get closer and closer together, close to the crack tip or to the tip of this singularity, and that gives rise to, let's call them large gradients, and on top of that, singular solutions. So in the case of a crack, which is nothing more than the Laplacian solved on an L shape with different angles. This angle is here. So here you see the angle is 0 effectively, or 180 or pi, 2 pi. So when that angle like this is such, or this angle here is very small, then you end up with an r over 1/2 singularity here, which means that the solution will look like a square root of r, meaning that the first derivative of that solution looks like 1 over square root of r, which goes to infinity when r goes to 0. And that's, of course, not what you like, because your numerical solution is not able to capture anything that goes to infinity, because it is usually based on polynomial functions. Here we are talking modeling, but in the discretization part of the course, we talk more about that, how to handle cases where you have these singular solutions simply by letting the discretization method know that you have these singular solutions present and adding that to the space of solutions. So this is what you can do using partition of unity, and we talk about that in the discretization course. Right, so that's what we talked about last time. And now I would like to continue, if I can. Thanks. That's very nice, because it started to be a bit vampire-like. Okay, so now, so in the course, I try to explain what happens for different cases. So you will be able to read that if you want to. Okay, so now let's move to right. Okay, so now let's just summarize a bit in which cases these elliptic, hyperbolic, and so on equations can be used, because we should be able to know what they are like. So elliptic, we already wrote down all the equations. So I'm just going to give you a few examples, because I know a lot of people come from different backgrounds, which does not make it super easy. Well, okay, so in math, really, what are the applications of these elliptic equations? So first of all, the key equation is Laplace equation. So this is the first thing. And well, second thing, what you do with that is you can derive what's called harmonic functions, which are, for example, sines, cosines, and so on. They are functions whose Laplacian is 0. And you have all the potential theory. Okay, what about in physics and / engineering? So we already talked about a lot of cases, but what would be other cases where we could have equations like Laplacian phi plus b of phi equals 0 plus boundary conditions? That would be typical elliptic equations. So what would that be? What would be typical examples? So we talked already about heat, well, not heat transfer, but at least heat conduction, not even conduction. Because there is no conduction, right? Yeah, maybe let's call it heat conduction, I guess, but without time. So steady state. So every time you have these elliptic equations, remember, this is always steady state. So that means d over dt is not there. So for instance, heat conduction, or what else? What could we get? Electrostatics. So I suppose you saw that, Coulomb's law, right? You have inelasticity. You have examples. Navier's equations, for instance. You have also Stokes flow. I don't know if shallow water equations work or not, but Navier-Lamé definitely do. Okay, so what about finance and economics? Because I know a few are in that area. So anything that has spatial equilibrium that is static, so static spatial equilibrium. So that could be for exchange of goods, for example, potential like formulation. Also for portfolios, you have this thing called mean variance portfolio states under constraints. So yeah, so you have quite a lot of stuff. So in biomedical engineering, you have anything that has to do with what? With diffusion tensors reconstruction for MRI, for example. So diffusion tensor reconstruction, this is an elliptic PDE inversion. So you basically have the solution and you look for the coefficients because you want to have somehow the amount of, you want to find the diffusion coefficient for water in the tissue, but you only have the image. And from that, you want to back calculate what are the properties based on that. You also the steady Darcy flow. So Darcy flow is just a porous medium flow. And you have lots of other examples. So anything that really has diffusion but doesn't have time dependence is going to be elliptic. So huge amounts of applications. You can also, in computer graphics, rendering. So rendering of images, you actually have to solve also these types of equations. You do some ray tracing, you try to figure out what the light would actually do on such a surface. And this is related to that type of equation. And it's very nice because these equations are very well behaved and very easy to solve. I mean, very easy to solve. It's all dependent on the case, huh? But it's, I would say, really the equations that will create the least amount of trouble for you. So if you can transfer your problem to an elliptic case, always do that, because you, and on top of that, this is not the subject of this course, but everything in math is proved. So you can show so many things in terms of the convergence of the numerical algorithms, how fast they converge, how slow, when they converge, when they do not, and so on. It's huge amounts that's known because it's easy to analyze, easier to analyze mathematically than the counterparts. And what is on top of that good is that you can use finite elements out of the box, no problem, and you won't have issues. You don't have stability issues, not too many. You may have problems with singularities, but that happens in any equation, not more or less in this one, because of the fact that the problem is in itself typically ill-posed. But you will see in hyperbolic cases, which is the next case, you can have also these singularities, but they are more hyperbolic, not bolic. So hyperbolic equations, they have something of a directionality. So you can think of them as waves, so wave-like. They are first order PDEs and not, well, typically, or second order with delta positive. But anyway, that the order is not really so important. The prototypes will be advection equations. For instance, the first order wave equation. So the first order wave equation will be you differentiate with respect to time a quantity you're interested in, plus A, which is a coefficient, times U differentiated with respect to space now, and the two should be 0. So this is called as linear advection. Again, if you write it more conventionally, that's partial U partial T plus A partial U partial X equals 0. And we may, if we manage, rewrite that a little bit using characteristics a bit later if we have some time and if I think this is a good thing to do. Then you have also the wave equation. So this is one advection equation, wave. So the wave equation need not be a first order. You can have second order wave equations. So for example, that would write UTT, so second derivative with respect to time, equals c squared, which is the velocity of the wave, Laplace in u. And so what does that mean? Well, it means that you have partial squared u partial t squared equals c squared times partial u squared partial x squared plus partial u squared partial squared u partial y squared if you're in 2D. So those two are exactly the same, just rewritten differently. And then, okay, yes, and then this c here is a parameter which is the wave speed. And that stuff is clearly gives you the velocity at which the wave is going to propagate. And that's related to these characteristics that I talked about earlier. And if you try to solve that using simple methods, well, typically you will fail, especially that very simple advection equation. If you solve that, and we show that in the discretization part of the course, using a simple FEM Galerkin method, you get immediately in one dimension already problems, especially when you are advection dominated. So, and that's the case for most problems with wave character. Because what happens is that depending on the velocity of the wave, you will compress the characteristics, or you will compress the solution towards a boundary, and then things will become squished, and then that will create large gradients or even shocks, which are discontinuities. That's why you have the sonic boom, because you press all the equipotentials along at one point. So part of the aircraft is traveling faster than the rest, and so that's why you have this sonic boom that's propagating. Is effectively due to, I will show you in a few minutes. Okay, now how do we solve? I didn't say how to solve Laplace equation, because you can solve that with anything. So elliptic equations, there is really no big problem solving that. You can use any numerical method you like, and it's going to work. Finite difference, finite elements. Of course, you can try to use discontinuous Galerkin if you like, but it's not going to give you a lot of benefit unless you want really very high order solutions. So really, there is not much to know about what to do there. So for hyperbolic equations, on the other hand, by the way, there are other applications before I move to the rest. So non-linear Euler equations is another application, which in other words is compressible flow. Compressible flow. Shallow water equations are also so shallow water equations are equations that you solve when you have a very thin film on a surface, and you want to solve the flow on that surface. This is quite different from that case where you have, instead of having a thin film, now you have a thick film, because if you're supposed to solve that, well, here you will use Navier-Stokes equations, but here you can safely assume that the only unknown is effectively the height of that film. And you boil everything down to a 1 degree of freedom problem, which is the height with respect to time. So h of t is the height of the wave that you are trying to follow or h of x, actually, in that case, h of x and t. That's what you are interested in. But here, if you have more bulky flow, you will not be able to make that assumption. It will be, in general, false, and you will use Navier-Stokes, which are much more tricky. And in the group, one of the guys Patrick has been working on how to transform the case of Navier-Stokes into the case of shallow water equations when you have a change in regime, so a regime shift. So for example, you might start with a flow which is bulky like this, but then that might transform into a shallow water case. And when that happens, you may not want to solve the full Navier-Stokes equations, which are very nonlinear and very difficult and super heavy. You may want to shift to a shallow water case. And this is what he's been working on in the last year, for problems where you, for example, want to clean a surface with a jet. So originally, the jet might be Navier-Stokes, but the surface, then once the jet hits the surface, the film becomes very thin, and you may be able to solve that using shallow water equations. So he has a way to change the model from Navier-Stokes to shallow water, and to change then back to Navier-Stokes when the flow becomes bulky again. It's very tricky stuff. So you know, if you're here, you may want to talk to him about this stuff, because it is super, very nice work that he's done. Okay, shallow water, traffic. You have also traffic equations that can be written like that. And yeah, okay, so now, as we said, the information propagates at finite speeds, and nonlinearities will cause two things. So what is important is that info travels at finite speed. So this is one thing which is different from here, where information travels at infinite speed. Okay, for elliptic cases, and then nonlinearities in these will create either shocks or rarefactions. So nonlinearities will create either shocks or what's called rarefaction fans. Okay, then now how to solve that? Solution methods, although that's more for the other part of the course, I'm still going to give you a bit of an idea. So, I mean, there is a lot in that question, so you cannot really solve it in 2 seconds. But what's important is that you want to ensure conservation. So you want conservation. So finite elements are not very good at conservation, because they are actually not conservative. They do not preserve exactly mass or volume. They will give you on average the volume conservation, but not exactly. And in that case, if you start losing mass and losing stuff, then your solution becomes complete rubbish after only a few time steps, because of that evolution and time travel of information. You cannot just make mistakes in time and hope that you will catch them back later. If you lose mass, you won't recover it. So you want conservation, and to have conservation, there are a few possibilities. One is finite volumes. about which I will definitely not talk because there is far too much to talk about, or the generalization of that, which is discontinuous Galerkin. So that's known as DG and FV, obviously. And what you do there, in fact, it's quite cool because you know that control volume we were talking about before is exactly what you do then. You just write the control volume equation, control volume after control volume, and that becomes your equations. So you just write the conservation equation volume per volume. Okay, so that's finite volume or discontinuous Galerkin. That's it. And then you have also in time, you have a lot of things to consider, like in terms of time integration, like Runge-Kutta and all of that. So I'm not talking about this, but you need to be precise about time integration and time. And for time integration, I'm not going to give you all the things you need to know, but all you need to know is you need to know that you need to satisfy the CFL condition, which is the Courant-Friedrichs-Levy condition. And that means that when you do time integration, why do you need to do time integration, by the way? It's because you have a partial something, partial t, but that thing for a computer means nothing, so you need to discretize that. And what does that become? It becomes a change in the something divided by a change in time, effectively. But the problem in hyperbolic cases is that that change in time is not arbitrary. You cannot take any arbitrarily large time step. You're going to have to march in time, and this is not a discretization course, so I'm not talking about this, but you are going to effectively do this. I have you at time step n. At time n, I want to move to time step n plus 1, and here I need to do some transformation to go from n to n plus 1. Either this is going to happen in one step, meaning it's explicit. If I know everything about time step n, I can find everything about time step n plus 1. That's possible. Sometimes you will need to solve a problem to move from, meaning invert a matrix to move from time step n to time step n plus 1. That's called implicit. In the second case, you preserve exactly the solution. In the first case, the more you compute, the more wrong you get, and the solution drifts away from the exact solution, and you lose pretty much everything. So you can imagine, that's very trivial to imagine. If you make a mistake at time step n, you will inherit that at time step n plus 1, and because you cannot verify the equations at any time, you just march forward. There is no moment in the calculation where the residual is minimized. You just march forward in time. So what is going to happen? Well, you're going to start by fitting the solution very well. Let's say that this is the exact solution. Well, you're going to do very well at the beginning, maybe, but you're going to make a small mistake, and then that error will simply accumulate, and after a while you will be completely off. So this is the explicit case, because at no time do you solve any residual minimization problem. You simply say, I know where I am, I know my velocity. You can move that in very easily to know, to think about projectiles, So I know where I am now, I know the acceleration of gravity, I know the initial velocity, I'm throwing a ball. So the ball, I will compute the initial velocity. So the position is u equals v times delta t. So v0 times delta t gives me u1, right? So I know now the velocity at, I know the position at the end of the first time step, right? The initial velocity was correct, everything's fine. Don't forget that we have gravity that's also pulling us down, so we will follow a parabola. At the end of the first time step, we are already incorrect because we did not verify the equation. So that's the way to think about it. If you solve everything explicitly, then any error will accumulate. So I would recommend solving everything implicitly, but of course, because it's much more expensive, people want to do to find intermediate solutions. So this is what we will talk about in the discretization course more. It's already in the notes, by the way. I wrote it already. And so now this delta whatever over delta t is not arbitrary. And the way to think about how to choose the time step is extremely simple. You can think about the domain as that. So that would be a typical element in your system. If you use finite differences, it works the same way. Finite elements is quite easy to understand. And then the wave is going to propagate along a certain direction. So this is going to be the wave propagation in a certain direction. So it means that at speed c is the speed or the velocity or the celerity of the wave. So it's going to take a certain time to cross the element. You can say that the element has a certain size, or the element, let's say, has an area A, so it has a characteristic length square root of A, for example. And if you know that the wave is propagating at speed c, then you know that the t, let's call it t0, that the wave needs to traverse the element is going to be the size of the element divided by the speed of the wave. And what you want is that your time step be smaller than the time it takes for the wave to cross any element. Because this way you have enough information. And intuitively, it's very easy to understand. If the wave goes faster than the time it takes for the wave to traverse one element, then you immediately see that you have a disconnect between your spatial discretization, which is the size of the element, and your time discretization, which is the time step. That's quite easy to understand because you can take it at the limit when, let's say, that your wave, that your time step would be equal to the time it takes for the wave to traverse the whole domain. This is the worst case. Then in one time step, the wave is already out of the domain and you've not computed anything in the domain because your time step is too large. So that would lead to instabilities and you would be completely unable to compute anything. So this is called the Courant-Friedrich-Levy condition, and that says that the time step must be less than t0, and t0 is h divided by c, and h is the characteristic size of the spatial discretization.
Is used for implicit methods or explicit methods?
Very good question. Only for explicit. For implicit methods, there is normally no time step constraint. Exactly. It is unconditionally stable, most of them. And you have a huge number of those methods, implicit Euler and beta method and alpha, beta, theta, whatever. So there are huge numbers of methods really behind that. But very good question. Yeah, exactly. This is for explicit. For implicit, you are, I think always, but I'm always careful to say always, because there are many things I don't know, that they are unconditionally stable. But what you can also do is you can do, in order to mimic, in fact, these explicit methods are sometimes used even to solve problems where there is no time dependence. So this is a bit of a trick. I'm just telling you this in parentheses. You may sometimes not want to use an implicit method because it's very slow. You need to solve a problem, assemble a matrix, and so on. So what people do is they take an explicit method, fake. So they add a fake time term to the equation. So they take Laplace, let's say, and they will add a partial u partial t in Laplace. That means it transforms the equation into now a parabolic equation instead of elliptic. But they add a viscous term, which makes the solution decay to the steady state solution faster. So effectively what they say is I do a fake time dependence, but I get rid of it by attenuating the time dependence by some sort of viscous damping. So this is cool because it gets you a solution to the steady state case by using an explicit time integration, but it's not so cool because one, it's explicit, and two, you have artificial damping, which in fact spoils the solution. Instead of solving a problem, you solve another problem. But this is very, very, very commonly used in computer graphics because they, until very recently, in fact, in my team, we were among the first with the team of Stéphane Cotin to do that, where they were solving implicit, I mean, they were always solving, they were doing the surgical simulation problem. So they want to cut inside a liver or brain or whatever and give feedback in real time. And until the time we worked with Adrien Courtecuisse, everybody was really saying, oh, no, explicit is the only way. You do explicit with that sort of regularization, and then it gives you a solution explicitly. But coming from mechanics, we didn't like that very much because you could never say what the error was. And this is not so satisfying. So we tried to solve that using an implicit method. And Adrien, doing his PhD, his postdoc, he worked on solving these equations implicitly by pre-computing, let's say, and the difficulty was that you are cutting. So it means that the stiffness is changing as you go. You're weakening the material, let's say. And so he computed a preconditioner to the problem using finite elements, and he inverted everything using conjugate gradient on the GPU. So you had finite element on CPU, GPU conjugate gradient running in the background, and he was solving asynchronously. So, you start solving for a certain state, you change the topology by cutting, but you still use the old preconditioner, which does not take into account the cutting or the contact or the change in topology or the change in shape or whatever you have as a change. So you can still compute with the wrong preconditioner for, let's say, 10, 20 time steps. And then you have a residual check. And if the residual starts to converge too slowly, then you recompute the preconditioner using the CPU, which is slow. So you don't want to do that too frequently. And at the same time, the GPU continues to compute, the conjugate gradient to look for the zero, and you do that asynchronously in parallel, and you shake hands from time to time between the two so that the solutions make sense. And he did that in 2004. At the time, GPUs were not really super developed, so it was really 2014. Sorry, so it was really, really cool. And since then, I think the methods have been used a bit more. We also introduced error estimates so that to refine the mesh in these real-time simulations in a smart way, not just random, because in computer graphics, they tended to simply add elements where the gradients are large, which is not stupid, but sometimes not really very mathematically logical. So yeah, there is a lot of work behind these. Okay, and then examples. Okay, so what could be examples of hyperbolic equations? Okay, so well, acoustics, anything that has waves, electromagnetics, so acoustics, electromagnetics is more or less the same thing. It's essentially Maxwell's equations, gas dynamics. So in traffic, you have conservation law for density, information propagation in supply chain, and so on. So, okay, supply chain. Again, shallow water equations, Saint-Venant equations, seismic waves. Saint-Venant, shallow water. So anything that really where things move, I mean, it's pretty clear. Acoustics, you would guess that cannot be elliptic. Elastodynamics, by definition, won't be elliptic. Gas dynamics, dynamics. So, you know, even without thinking, you can immediately know how things will look. Okay, now let's look a bit at parabolic equations, which are, they are a bit of a mixture of those two, because you will have a diffusion term, but you will have also a time dependence. So it's going to be diffusive plus time dependence. So the canonical example is Laplacian u with some coefficients. In fact, it can also be nonlinear, plus b of u, which is the body force term, equals partial u partial t, which is the change in time. You can also write it ut, and sometimes you write it like that. And so that guy is the source, that is the diffusion, and that guy is the time dependence. So that's the change in u over time. Okay, so examples of that: Fokker-Planck equation, Black-Scholes after log time change. So it could be also useful in finance, because the Black-Scholes is used everywhere. I mean, everybody knows it's wrong, but it's still used by, you know, management firms and hedge funds and so on. Since everybody uses the same one, probably that's why it's predictive. But in reality, that's clearly not something that's really predictive in real life. So what do we know here? So information propagates also at infinite speed. Propagation at infinite speed. Because you have a diffusion, you have a very smooth, so every time you see this guy, the Laplacian here, you can always think that the solution will be smooth. This really smooths the solution, okay? And that's why you don't have all that mess associated with stability and so on. It's much less problematic. Because what does that do? Well, it computes on the right, on the left, takes some average, does that twice, you know. So basically, anything that wants to grow is immediately wiped back down by something which computes its derivatives, right? Because it forces the derivative to be, the second derivative to be relatively smooth, right? Because of the b of u, which is in here. And unless this b of u, which is the source, is really ill-behaved, like singular or exponential or whatever, then your solution can start misbehaving. But unless that's the case, you know, things will be good. Okay. Okay, how do we solve that? We can solve that using pretty much everything: finite difference, finite volume, finite elements, implicit methods like backward Euler, Crank-Nicolson, or anything. Right? So that's quite easy. Did I want to talk about that? Yeah, so that's good, because, for example, if you have really, I mean, most cases will fall into, I mean, not most, but a lot of cases fall into that case. you know, in biology, you have things like chemotaxis or any coupling between chemical reactions in a cell. For example, you have metabolic rates and so on. So if you have bacteria that grow in an aquifer, same thing. It's going to be effectively bacteria eat oxygen. As they eat oxygen, they produce bacteria. So you have the oxygen flux inside should be equal to how much the bacteria eat the oxygen. And then by eating the oxygen, they produce more bacteria. So you have a source term of these bacteria, but then the bacteria die because after a while they can't live forever. And, or maybe they just don't have oxygen. So you have some sort of, you know, ischemia, you know, so not enough oxygen. And so they die. And once you have this necrosis, then you have to take that into account and so on. So everything can be written like that, more or less. So it's super useful to know how to solve those and at least how to recognize them. Then there are also some really cool equations that you can look at in terms of parabolic. I can't. Okay, so there are some pattern formations sometimes that are called Turing patterns. It's also related to biological morphogenesis. And you can sometimes get that when you have, so partial TU plus, actually, no, let's put it on the other side. So equals some diffusion D times Laplacian U. So this is Laplacian U plus some reaction term, and you have different species. So what can happen is that diffusion is going to destabilize a stable ODE fixed point, and you have what is called diffusion-driven instabilities, which is counterintuitive because we just said that diffusion stabilizes things. But when you have several species together that are being coupled, so as you can see, this is here a vector, U. So that means that you don't have only one unknown now, but a vector of unknowns. And that can complicate things. So if you're interested in that, we can talk about it, maybe want to look at it for a project or something, because it can be quite cool. So it's called two-species model activator inhibitor, or also known as Schnackenberg or Gire-Meinhardt kinetics, and so on. Laplace-Beltrami operator, and so on. So it's it can be cool to look at. So if you're interested, let me know. We could do that. Then you have other examples like flow in porous medium. So I know some of you could be, I can't write today. I don't know what's going on. So for flow in porous medium, you can look at it in many ways, but one is known as Darcy's law, in which case you have the velocity called v, which is minus some coefficient over mu grad p. Then you have a time derivative with respect to phi rho plus grad of rho v equals q. So don't worry about all the details in there, but basically means that the velocity can be related to the change. The velocity can be related to the change in pressure, so the gradient in pressure. And that has to do with conservation of mass. So you have basically conservation of mass and the velocity related to the pressure change. And that's it. So I think what I do is I will stop here anyway, because I think it's enough. And if you like, yeah, in my team there is well, for now, one student, Ingrid, who works on something which is very similar to that. It's astrocyte models in the brain, and the equations are very similar. So it's all about reaction, diffusion, and so on. So if you talk to her now, you know what type of equations she's solving. And yeah, thank you. I hope it was a bit informative. Sorry for all the blah blah. I hope it was fine. And thanks online for everybody who's here. And see you, I don't know when, whenever the allocator decides that the next time is the right time. And yeah, have fun in the meantime.